Hi there, this is Heath. We're starting a brand new chapter today. This is section 15.1. We're looking at double integrals over rectangles today. Let's go ahead and get started. When we first studied integration, we started with the idea of a Riemann sum. The Riemann sum allowed us to approximate the area of a region by dividing that region into rectangular strips, and then doing some sort of estimate of the height of each strip, and then adding the areas of each of those little strips together. That's the idea. Let's try an example just of a two-dimensional Riemann sum. We're going to use the midpoint rule with delta x equals 2 to estimate the integral from 1 to 7. So from 1 to 7, just this area here. See if I can get that line to come out almost vertical. All right, and then 7. There we go. All right, I can't draw, but we'll give that a try. Use the midpoint rule with delta x equals 2. So our subdivisions are going to be 2 units wide. So we're going to go here at 3 and here at 5. And these are going to be our regions. Since we're using the midpoint rule, we use the midpoint between 1 and 3, which is 2, to generate the height of our first rectangle. Then we use the midpoint rule for the second rectangle, which is at 4. And then we use the midpoint rule for the third rectangle, which is over here at 6. Okay. So we have 3 rectangles. For the first rectangle, the width is 2, which is the same as your delta x. The height is f of 2, which is the midpoint between 1 and 3. And f of 2 is 2 squared minus 8 times 2 plus 17, and that equals 5. And so the area is 2 times 5, and that equals 10. So that's for the first rectangle. For the second rectangle, the width is 2. The height is f of 4. So that would be 4 squared minus 8 times 4 plus 17. And that equals 1. And so the area is 2 times 1, which is equal to 2. And then we've got to find a way to place to squeeze in the third rectangle. And I don't have a lot of room today because I want to leave the calculator open. So the third rectangle the width is 2. The height is this time f of 6. And I'm going to leave out the calculations here. The 6 is 6 squared minus 8 times 6 plus 17. And that's 5 again. And so the area is equal to 2 times 5, which is equal to 10. And so this region has an area that's approximately 10. This region has an area that's approximately 2. This region has an area that's approximately 10. And so this integral is approximately 10 plus 2 plus 10, or 22. Okay? That's using the midpoint rule. If we had used a left-hand sum or a right-hand sum, we would have gotten a different estimate. But because this shape is symmetric, a midpoint rule looks good because the error in the first rectangle and the area in the second rectangle kind of balance each other out. Okay? So let's move on and try this in 3 dimensions. We're going to use a Riemann sum with delta x equals 2, delta y equals 2 to estimate this rectangle. And we're still going to go ahead and use the midpoint rule. I didn't specify that in the problem, but we're going to do this anyway. So let's draw a picture of what's going on here. We're looking at the rectangle bounded between 2 and 4 on the x-axis, and between 1 and 5 on the y-axis. And so that's this rectangle here. And since delta x is equal to 2, that is the width from 2 to 4. We only have one subdivision in the x direction, but delta y is equal to 2, so we also have a subdivision in the y direction. So we're going to use these 2 rectangles to estimate the volume. We also have this shape here, which, I can't draw this. Let me use a different color for this part. But there's some graph over this rectangle. And what we're looking to do is estimate the volume of these rectangular boxes now. And the volume of a box is the length times the width times the height. So we have 2 boxes. I'll go back to black here. So for the first box, which I'll number these boxes 1 and 2, the length and the width is delta x, which is 2. The width is delta y, which is also 2 in this case. And the height is f of the midpoint. So the midpoint of this rectangle is halfway between 2 and 4. So x will be 3. And halfway between 1 and 3, so y will be 2. And so we need f of 3 comma 2. So that's negative 2 times 3 squared minus 2 times 2 squared, which is 2 squared, there we go, plus 12 times 3 plus 8 times 2 minus 21. All right, so what do we get here? We get negative 2 times 3 squared is negative 18. So let's see if we can make this happen. So we're going to make this a negative 18. And then 2 times 2 squared is a negative 8, so we're going to subtract 8. And then we're going to add 12 times 3, so that's going to be plus 36. That takes us up to 10, plus 8 times 2, so that's going to be plus 16. And then minus 21. And so we get a height of 5. And what happened to my cursor? There we go. And so the volume is the length times the width times the height. 2 times 2 times 5. Well, that's 20. That's an estimate for the volume of this first box. So let's look at the second box now. Again, the length and the width are your delta x and your delta y. Your height in this case is the value of the function at the midpoint of the second rectangle. So again, x is halfway between 2 and 4, which is 3. And y is halfway between 3 and 5. This time y is 4. And so that's plug in 3 and 4 into this function. And let's go ahead and do those calculations. All right, so we start out with negative 2 times 3 squared. That's negative 18. All right, and then we take negative 2 times y squared. So negative 2 times 4 squared is negative 32. So we're going to subtract 32 this time. Then we're going to add 12x, so that's plus 36. And then we're going to add 8y. 8 times 4 is 32. And I made a mistake because I didn't hit my plus sign there. So let's start that over again. Negative 18 minus 32 plus 36 plus 32 again minus 21 gives me a height of negative 3. So my picture is not very good because actually this second rectangle has a height of negative 3. It's actually dips below the xy plane and not above the xy plane. So my picture is not to scale, but that's okay. The volume then is 2 times 2 times negative 3. And that's 4 times negative 3 is 4 times negative 3 is negative 12. And so the total volume is 20 plus negative 12, which is equal to 8. So this is a very crude estimate because we're only using 2 rectangles. But we're getting a crude estimate of 8 for the volume. All right. So just like it was in the two-dimensional case, it should be clear that if we used smaller values for delta x and delta y, we would get a more accurate approximation. We would be using more rectangles. We would be sampling the height of the graph at more points. That increases the number of calculations. But this is something that we could automate using a spreadsheet or a short little program to loop through all the different cases. And so we can get a very accurate numerical result using a large number of rectangles and a small delta x and delta y. And we can get a good numerical approximation without ever having to take an antiderivative. But when we have to work this out by hand, we don't want to do lots and lots and lots of rectangles to get an accurate estimate. We would like to be able to integrate this. So suppose we wanted to find the exact value for the volume in example 2. We can do that by integrating in one of the directions, either x or y first, and then integrate in the other direction after that. We call this a double integral. So let's try this example. This is the same region we were looking at before, where x goes from 2 to 4, and y goes from 1 to 5. We're going to integrate over that region. So this is R is the region bounded by these rectangles for this function here. We're going to take the derivative with respect to the area of the little tiny rectangles, not triangles. Area of rectangles. Okay. We won't use this notation very often. We'll use a different notation, which we'll see in the next example. But let's talk about what's going to happen here. So what we can do this by integrating in one direction and then the other. And so let's do the x direction first. So if we integrate this from 2 to 4, negative 2x squared minus 2y squared plus 12x plus 8y minus 21 with respect to x. We're taking an antiderivative now, but with respect to x. So when x is the variable, we do an ordinary antiderivative. This becomes negative 2/3 x to the third. But when there is no x in the term, we treat this term as a constant, just like we would do when we were taking the derivative. The derivative of a constant is 0, but the antiderivative of that constant is that constant times x. The antiderivative of 12x is 6x squared. The antiderivative of 8y is 8yx, or 8xy, either one, minus 21x. And we're going to evaluate this at 2 and at 4. Okay? To simplify this a little bit, I'm going to do the evaluations that don't have y in them first. Okay? So I'm going to plug in 4 to this term and this term and this term. So let's see what we get over there. So the first term would be negative 2/3 times 4 cubed. That's negative 128 thirds. Have to make that negative. Plus 6 times 4 squared, so that's 6 times 16, that's plus 96. Minus 21 times 4, so that's minus 84. And so that's negative 30 2/3, or negative 92 thirds. And then let's look at what happens to the y terms. This is going to be negative 8 times y squared. So I'm going to just use a different color for this. Minus 8y squared. And then this term is 8 times 4 is 32y. All right, now we have to do the same thing for 2. We have to plug in 2. So we're going to do all of the x terms first so that we'll get a numeric value, and then we'll look at the y terms after that. Okay, so negative 2/3 times 2 cubed is negative 16 cubed, not negative 16 thirds, excuse me. So 16 divided by 3, make that negative. Then the next term is plus 6 times 2 squared. 6 times 2 squared is 24. and I did the same thing I did before. 16/3 change the sign, plus 24. There we go. And then minus 21 times 2. So that's minus 42. And we'll get negative 23 1/3. That's negative 70 thirds. Okay? There we go, negative 70 thirds. And then we have these other two terms. The y squared term is going to be negative 2y squared times 2. That's negative 4y squared. And then the green term is going to be 8 times y times 2. That's 16y. All right. So we have to subtract this out. Subtracting a negative 70 thirds is just adding 70 thirds. So we get negative 22 thirds. And subtracting negative 4y squared is adding 4y squared. So we have negative 4y squared. And then 32y minus 16y is plus 16y. So we have finished doing the integral with respect to x, but we still have to integrate now with respect to y. So then y. This time we're integrating from 1 to 5, and we get negative 22 thirds minus 4y squared plus 16y dy. Excuse me. All right. Negative 22 thirds y is, the integral of negative 22 thirds is negative 22 thirds y. The integral of 4y squared is 4y cubed over 3, so 4 thirds y cubed. And the integral of 16y is 8y squared. And then we have to evaluate that from 1 to 5. All right. So when we plug in 5, we get negative 22 thirds times 5 is negative 110 thirds. And then 4 thirds times 5 cubed is 4 times 125. That's negative 1,000. No, negative 500, not 1,000. Thirds, plus 8 times 5 squared. So that's 8 times 25, and that's 200. Minus, and now we're going to plug in 1. So that's negative 22 thirds. Minus 4 thirds times 1, plus 8 times 1 squared. Okay? All right, let's add all of this together and see what we get. So let's do the thirds first. I'm going to do the 200 and the 8 at the end. So we're going to do 110 thirds. That's negative 110. Minus 500. Minus a negative 22 is plus 22. Minus a negative 4 is plus 4. And that's divided by 3. And then we're going to add 200. And then we're going to subtract 8. And our answer is not very close to our estimate. Our estimate was not very good. But our final answer turns out to be negative 2 2/3. Okay. But we've calculated the exact value of this integral by integrating in one direction and then integrating again in the other direction. So this is the notation that we're most likely to see for a double integral, where we see the boundaries in the x direction written out and the boundaries in the y direction written out. These are nested, and so these boundaries go with this variable, and these boundaries go with this variable. That is, the order isn't left to right, it's outside to inside. Okay? And so if you want to think of an imaginary set of parentheses here, you can. We don't write the parentheses usually, but you can certainly imagine one of those. And so what this is saying is do the integral with respect to y first, from 0 to 4, and then when you're done with that, do the integral with respect to x, from 0 to 2. Okay? So let's see if we can make this happen. So we're going to do y first. And we're looking at the integral from 0 to 4 of 2x plus xy dy. The integral of 2x with respect to y is just 2xy. It's the integral of a constant with respect to y, so we just gain a y. The integral of xy with respect to y is 1/2 xy squared. And we're going to integrate that from 0 to 4. Again, I'm plugging in 0 and 4 for y, not for x. So when I plug in 4, I get 2x times 4 is 8x. When I plug in 4 here, this is 1/2 x times 16. That's also 8x. When I plug in 0, I get 2x times 0 and 1/2 x times 0. And so my answer is just 16x. Now I take this answer and I integrate that with respect to x. So y first and then x. So we're going to integrate 16x from 0 to 2. So the integral of 16x is 8x squared. We'll plug in 0, we'll plug in 2. 8 times 2 squared is 32. And 8 times 0 is 0. And my final answer is 32. Okay? This is an example of what we call a double integral. We're integrating a function over the region where x goes from 0 to 2 and y goes from 0 to 4. And we're looking for the volume of the volume that's underneath that function and above this rectangle. And that volume, in this case, is 32. Okay? So the big question I want to go over is, what if we had integrated x instead of y first? Could we change the order? And so let's try it and find out. So this is example 4 again, but notice I've changed the order now. I've put the x on the inside and put the y on the outside. When I change the order of the variables, I also change the boundaries because, again, the inside boundaries match with the inside variable, and the outside boundaries match with the outside variable. So we're going to do x first this time. So we're going to integrate from 0 to 2, 2x plus xy with respect to x. The integral of 2x is x squared. The integral of xy is 1/2 x squared y. going from 0 to 2. When we plug in 2, this is going to be 4. When I plug in 2, this is going to be 1/2 times 4. That's going to be 2y. Then when I plug in 0, this is 0, and this is also 0. And so we get 4 plus 2y. We take that answer and they integrate that with respect to y. And this time y goes from 0 to 4. 4 plus 2y dy. The integral of 4 is 4y. The integral of 2y is y squared. When I plug in 4, 4 times 4 is 16. 4 squared is also 16. When I plug in 0, 4 times 0 is 0, and 0 squared is 0. And so we also get 32 this way. And so that's not a coincidence. When we change the order of integration, we usually get the same answer. The only times the order of integration matters, there are two cases, and we'll talk about those on the next slide. This is a result called Fubini's theorem. It's the integration counterpoint to Clairaut's theorem. We talked about Clairaut's theorem last week. That when we took the derivative with respect to two variables, the order didn't matter as long as the function is continuous, as long as we don't have certain problems with continuity, and as long as the limits of integration are constants. Then the order of integration doesn't change the answer. What I mean by constants is later on we're going to see some examples where the inside variable might not go to 2, it might go to, for example, 2y. And then that will describe a region that's not a rectangle, but it will be a region that has a line for the top that has a slope. And so that would be like a trapezoid region. Excuse me. Sorry about that. So we'll look at those next time, but we won't do that today. But as long as the boundaries are constants, then and the function is continuous, then the order doesn't change the answer. Sometimes that will be a time saver, and I want to go ahead and show you an example now where the order will be a time saver. So this is going to be our last example for the day. We want to solve this problem. Okay? Integrate x cosine of xy dx dy, where y goes from 0 to 1 and x goes from 0 to pi over 2. So right now, again, I'll put my parentheses here. So what the problem says, to do x first. But that means that we have to integrate x cosine xy with respect to x. And I have an x here and an x here. And we can do that, but we have to use integration by parts. Integration by parts, maybe you remember, is that the integral of u with respect to v is u times v minus the integral of v with respect to u. U dv equals uv minus v du. In this case, we're going to let u equal x and dv equal cosine of xy. Then when we take the du just becomes 1, and we'll just have a trig function without an x over here. But integration by parts, well, we can do that, but I don't want to do that if I don't have to. So even though the problem says to do x first, we know by Clairaut's theorem that as long as this function is continuous, and it is, because cosine is continuous and multiplying by x won't change that, then we can also do this in the other order. We can put the pi over 2 on the outside, 0 to 1 on the inside, x cosine of xy, with respect to y first, and then with respect to x. And let's see how much simpler that is. So we're going to do y first. So the integral from 0 to 1 of x cosine xy dy. This is just a constant times cosine of a constant times y. Well, a constant we can pull out to the front. I can actually just pull out the x to the front. And the integral of cosine of a constant times y, the integral of cosine is sine. And the x comes out as a 1 over x. That's a u substitution problem, where if u equals xy, du is equal to x dy, and so dy is equal to 1 over x du. That's u substitution instead of integration by parts, and that's not so bad. And in fact, this x, I'll use red for canceling, and this 1 over x cancel each other out. And so I just have to now plug in 1 and 0. When I plug in 1, I get the sine of x times 1. When I plug in 0, I get the sine of x times 0, which is just sine of x. And now I take this answer here, and I do x second, so then x. X goes from 0 to pi over 2, sine of x. Well, sine of x, the integral of sine of x is negative cosine of x. Plug in pi over 2, plug in 0. When I plug in pi over 2, I get 0. When I plug in 0, I get negative 1. Negative cosine of 0 is negative 1. 0 minus a negative 1 is 1. And so that's our answer. And instead of doing integration by parts, which is what we would have had to do if we did x first, because there are 2 x's in this problem, instead we only had to do u substitution, because when we did y first, there's only 1 y in this problem. And so that simplified the integration, because we get to do the simpler value of variable first. Okay? So this wraps up today's material. What we're going to do tomorrow or Monday is being able to set up a double integral for a region that's not a rectangle, so that the boundaries of the region won't be constants. And we'll talk about how to do that, why those examples are a little bit more complicated, and one of those reasons is what we just saw here, is that we can't automatically just change the order of integration if the boundaries aren't constants, and so we can't use Fubini's theorem. We'll do those examples on Monday, but in the meantime, have a great weekend. Take care.